Hello, everyone. This is Sherif I am with the School of Computer Science, University of Windsor, and today I will cover practical challenge of applying machine learning in cybersecurity. Before we cover the practical challenge, I think it's important to agree first, why is machine learning for cybersecurity? Well, nowadays, machine learning techniques are used to build all kinds of cybersecurity solutions. We can see this in access control system, intrusion detections, fraud detection system, and so on. And it's unlikely in the last 3 years, for example, if you are reading any articles or research paper for cybersecurity solution, that this paper will not contain one or more machine learning techniques. The general belief is that machine learning will help in improving the efficiency of the systems, reducing the cost of cybersecurity operations, and assist the analyst in their daily tasks and so on. However, what we think is that the reality is that cybersecurity, machine learning for cybersecurity is not really a silver bullet. It's in some cases, and practical example exists where the malicious actors or the hackers, they actually utilize machine learning to execute a very sophisticated cyber attacks. So it's kind of a double-edged sword. However, this was not the start of our research. We start from the idea of, what we notice is that there is a significant difference between the performance of machine learning or cybersecurity solutions that apply machine learning, usually in the lab and the literatures, and when we deploy this system in the production environment. There is a huge difference in performance if we look at the accuracy, for example, or the scalability of the system and so on. So starting by this question, we try to understand why there is a gap between what we can see in the lab, what we can see in control environment, and what we see in production. And what we did over the last 3 years is we started looking at the challenges, and one of the most surprising one was machine learning interpretation. So what is machine learning interpretation? Now, interpretation is a process of giving explaining the decision made by a machine learning model. So, for example, if we have a machine learning model that use, if we have a malware detections, a system that to detect malicious binaries that use machine learning, we would like to know exactly why the system decides that a given binary is malicious and another one is benign, it's not malicious. Basically, in a human understandable way. For example, I use this to explain the idea. Okay, if this is a duck, why it's a duck? Well, simply, this is the expected level of interpretation. It walks like a duck, it swims like a duck, quacks like a duck, then that's why it's a duck. That's it. So what we found when we start talking to different cybersecurity analysts and people in the industry, they actually don't prefer a lot machine learning solution at that time. And usually they will rely on rule-based and signature-based. And in one case, I think one of the teams, they mentioned that for their fraud detection system, they cannot use deep learning. And why? Because they cannot explain why a specific transaction was classified as a fraud or not. It was very interesting. So they use rule-based or other less sophisticated solution. They sacrifice the performance of a more sophisticated system just to be able to explain the decisions. And this is mainly because most of the time, detecting a malicious event for the cybersecurity teams or the analysts is not the end of the story. It's actually the beginning. That's where they start the analysis. And machine learning interpretation in general is an open challenge. It's not only for cybersecurity, but it's a must or an important requirement for machine learning to be accepted in production level cybersecurity systems. That's at least our opinion. So in the last few years, the topic itself of the ability to interpret machine learning decisions in cybersecurity received a lot of attention. And what we found that in general, solution for interpretation, machine learning interpretation, could be classified into two categories. Some solutions are model specific. That means they work for a specific model. So this interpretation techniques will work with random forest, will work with linear regression, with deep learning. It's not going to work with other techniques. Okay, and usually this techniques require understanding of how the model works internally. The other techniques, which is more interesting, are the model agnostics, but they are more difficult. Those interpretation techniques doesn't require, they work with any model. They treat the model as a black box. They don't need to understand, for example, for a deep learning or a neural network, how many layers are there, what kind of activation function we have, what is the depth of the random forest, or how many trees are there. They don't actually need any of those. Now, what we found also very interesting is that interpretation solution will always be domain specific. You can have a model agnostic techniques that can explain different machine learning models, right, without the need to understand the internal behavior or internal operation of the machine learning model, but it has to be domain specific. So what we did is, over the last 2 or 3 years, we were working on trying to see if we can use the existing interpretation technique or customize some of them to be able to interpret the decision made by malware detectors that use machine learning. So in one experiment in our paper here, you can find we tried different techniques, deep learning, random forest, linear regressions, to build a classifier, a detection system that can classify different type of malwares using n-gram analysis. And we apply different model-specific interpretation techniques. And we successfully were able to link the decision made by the model, let's say it's a malicious or a ransomware, for example, and we were able to trace back the decision to an exact block of code or instructions inside the binary. And this is a part of the code that result in the assumption of that triggers the machine learning model to say that this is a malicious binary. And in some cases, this part was usually non-malicious at all. Like the part of the block of the code could be in the header, for example. So, which usually will result in false positive. So actually interpretation could help also in debugging and understanding the problem within the system. However, again, this technique could be utilized by malicious actor to reverse engineer the model and, of course, take advantage and bypass the model. The source code and the papers are available in this link, and I can give it if you contact me directly. The second challenge was very interesting, which is adversarial machine learning. So what is adversarial machine learning? Adversarial machine learning happens when the malicious actor or the attacker craft a specific input to the machine learning model, hoping that the machine learning model will fail in classifying this input sample correctly. Basically, if it's a classification problem, then it will give incorrect label. If it's a regression, it will give like out of range score, something that's not expected. Okay, so here, for example, a machine learning model, the input is an image for a duck. However, the attacker will add to this image another image with some well-crafted selected data, and this will result in the machine learning model to fail to detect that this is a duck photo, just a horse or anything else. Now, in reality, adversarial machine learning, from the attacker perspective, either to accuse the model to make a mistake, fail to detect that this is a duck, this is a malware, this is a fraud, this is a money laundering transaction, something like that, or, and this is a more sophisticated example, is to trick the model to generate a specific output, a specific label, right? Chosen by the attacker. For example, in access control system, it will trick the model to believe that this is the voice signature or the fingerprint signature for a specific user who has access to the system. Now, the good news is that the second scenario, where the attacker choose a specific output, right? So craft the malicious input to generate a specific output, is actually very difficult. In our opinion, it's not even practical, at least based on our analysis. The first case, which cues the system to do mistakes, it's very easy. It's extremely easy to the point that the attacker himself doesn't need to understand the machine learning model or the details. He doesn't need background in machine learning. Okay, that's very interesting. So what we start trying to understand here is what kind of defense mechanism we could use against this. Now, here's the thing. First of all, in our opinion, adversarial machine learning is it new and practical problem? Well, it's practical because the attacker can take advantage of the system. It's not really new. If you think about it, it's not a problem related to machine learning itself. Basically, it's a classical problem in cybersecurity where the attackers can take advantage of any system by finding weakness, right? it's not really a new challenge because evasion attacks itself exist in the cybersecurity domain a long time ago, even before the machine learning and AI become a mainstream as nowadays. So ideally, what we try to do is, because the common practice for adversarial machine learning nowadays is more training with adversarial examples. So you train the model to see the crafted attacks, right? Well, we disagree. This approach is not really practical in our opinion, because there is no way you will cover all the possible attack space, right? The reality. But anyway, the solution, in our opinion, should not be by changing or overtrain the model. Actually, in many cases, if we consider other best practices in cybersecurity, like security layered security by design, in-depth security, you could actually prevent those attacks very easily without the cost of retrain or change the machine learning model itself. So we start trying to understand how fast an attacker or a malicious actor could probe the system, how long it will take him to bypass the system, how many samples he could present. So basically, we try to understand the effort, how much effort, computational power, time, even resource like money, the attackers need to put in place to be able to attack the systems. And we start looking at other solutions that doesn't require a defense mechanism, that doesn't require the attacker that doesn't require us to change the model to prevent the attacker from bypassing the system. Now, we did two studies. The first one, which the first case scenario, where we just try to evade detections. You are not trying to trigger the model to generate a specific output. So to do that, we build a fileless malware using JavaScript. So basically what we look, and that was a very interesting experiment, we look at the existing new features in JavaScript and HTML5, and those benign features like WebSocket, web storage, web worker, service workers, and all of this, we look at those features. All of them are benign and very useful, of course. However, you could combine them in a certain way to generate a very sophisticated malware that in our experiment, in the open source malware detectors, JavaScript, of course, malicious application, web application detection, malicious web application detections, none of those tools were able to detect the malware. And when we think about it, we figure out, okay, why they cannot do that. Even the one that use rule-based or AI doesn't matter. So the problem was very simple. The features themselves are benign, but the combination is malicious. So basically, the ingredients are healthy, but when you combine them in a certain recipe, they become poison, right? So that's what the challenge here. So it's very easy. The engineers or the developer who built this didn't know the detail of the machine learning models. The other scenario, which was a sophisticated one, we tried to use adversarial machine learning to generate, to craft a biometric sample, like let's say fingerprint or voice signatures, whatever, to bypass an access control system that uses this biometric technology. And this was not practical at all, because eventually we actually had more than 22 students or 22 developers building different algorithms to generate this fake biometric sample. The problem is that no one were able to break into the system or generate the right sample to bypass the system in the first or the second or even the fifth attempt. Some of them take 200 trial and error, right? So in reality, this is not going to happen. Access control system, usually after one or two or three failure attempts, they will lock down. If you are using multiple authentication system, multi-factor authentication, this attack is not going to happen. So as you can see, this kind of adversarial attack that require you to generate, to trick the system to generate a specific output is not really practical. The source code for the malware and the data for the biometrics are also available on our website, and you can contact me directly. The third and the last challenge is best practice. Best practice, the current best practice in machine learning regarding the life cycle, collect as much data, do feature engineering, train, crossover, and and the pipelines. Well, those current best practice, not necessarily the best practice when it comes to applying machine learning for different cybersecurity problems. The fact that the current trend use monolithic architectures in terms of the model itself. So you collect a massive amount of data to train the model, do the feature engineering, do whatever, and then build the machine learning model, train, deploy, and so on. This is not valid for different issues. First, the data, this huge amount of data is not available. It's not only the data requirements. Sometimes the patterns are varied and unique. The features are not robust enough, right, to do feature selection, even if the data is available. So adaptability and the scalability of the machine learning model is very important. And we show that in one of our experiments with behavior biometrics. So we find some of the existing production system that use behavioral biometrics for continuous authentication. So behavior biometrics think like gate, keystroke, voice, but mainly for continuous authentication. So those systems will try to validate the identity of the subject during the login session, not at the login time only. So even after you log in, your online session, still monitoring your behavior. Anyway, so we look at the work in the literatures, and we find that in general, the accuracy of those systems are very high, above 90% for continuous authentication, and they have the data, they have this, but here's some of the limitation. If we try to apply the system in production, the result will drop a lot, even 20% less, sometimes 40, sometimes the result was not acceptable at all. Well, here's the mistakes. In some cases, they will do the following. They will say, okay, you know what? They do what? The data set, they train with 80%, they test with 20%. They ask the user, for example, in the case of login keystroke, to enter the password 400 times to collect the data, the same password 400 times. And then after the 400 attempts, they use 80% of the 400 attempts to train the model and 20 to test, okay, is it gonna detect the user or not? There's no way the user after how many, like, it's not practical to ask anyone to be able to train his model using this. Most of the time in the literature also they use what? They use multi-class classifiers. In access control system, the reality is that multi-class classifiers are useful for identification, but not for verification. There are many cybersecurity problems where you need anomaly detectors or one-class classifier. You only see the positive sample, you don't see the negative. You only see the normal, you don't see the abnormal. So even reporting a result with multi-class classifier is not valid. The signatures, the behavior of the user change over the time. And there are well-published studies that show this, especially for behavior biometrics. So the fact that you are not retraining or assuming that the retraining will happen once is not correct. However, in the production system, there are some well-known systems that work well. So we tried to compare, and what we did, we were able to replicate an accepted accuracy, right, under the production level conditions, production environment conditions. However, what we found out that the best practice in applying machine learning, the general best practice, is not anymore best practice when you do this for cybersecurity. Now, for here, again, so our paper toward engineering reliable keystroke biometric system explains the detail of this. The source code and the data is available on our GitHub repository. Here is the reference that I used today. Most of this work, I think there are 3 papers already out, published already. 2 are still still submitted. However, if anyone would like more information or have questions about the topics, the different challenge, and here I just want to mention that those are the most important practical challenge in our opinion. However, there are more. We can discuss more examples during the online session. Thank you very much.